Due to the special situation that is that we have online classes for the next 2 weeks, I spontaneously decided I'm going to talk about RoboCup. That is robot, the world competition in robot soccer. So I will talk about this competition and of course the background and the history. In order to understand what is the RoboCup and robot soccer in general about, we have to go back to the year 1997. In the year 1997, the best computer for the first time played better than the world champion, the human world champion in chess. The best computer at that time, or the computer that did that, was a product from IBM, Deep Blue, and the world champion in chess at that time was Gary Kasparov. And that gave rise to the question, if chess, which is considered a game for intelligent people, so if we know a human who plays excellent chess, we would assume this human is also very intelligent. So if this is about intelligence, and we have a computer that plays excellent chess, then this gives rise to the question, why if this computer plays excellent chess, why this computer cannot do simple everyday control tasks, like driving a car or controlling a human bringing some milk out of a refrigerator or something like that. Yeah. And so people came up with this idea, okay, maybe for these everyday tasks, chess is not something like a good benchmark. Maybe we should have another game as a benchmark that is more similar to our everyday environment. And for this reason, a Canadian professor came up with the idea, okay, why not use football, soccer, as a benchmark for intelligence. And this idea was brought to a bigger picture by a researcher from Sony, Hiroaki Kitano. Yeah, he was really working at Sony at that time, and he wrote a huge proposal to the Japanese government, and the core target of this proposal was to defeat the human soccer world champion with the best robot team in the year 2050. So this is still the core goal of RoboCup, and this is basically also some concept on which everything is oriented inside this RoboCup competitions, where they all argue, okay, how we should orient our competitions on and so on. Of course, research-wise, this was embedded, and embedded is here the word, embedded in a bigger picture, and that is the embodiment concept that was established in the years before. And there the idea is a computer alone, without a body and without sensors and actuators, cannot really interact with an environment. And we had here the Breitenberg vehicles before. I talked about them in other classes, that they appear to love light or hate light and so on. So kind of behaviors that arise from very simple electric circuits and their shape, the shape of their bodies. So in other words, that the structure of the body is essential to develop some concept that might appear from outside as intelligent. and this is called the embodiment concept. And over the years, of course, this idea attracted many very excellent researchers. Here I put some, if you might say, arbitrary collection of them. This is the famous Professor Breitenberg who came up with this vehicle and wrote this book, Vehicles, already in the 1970s. And then we have here Rolf Pfeiffer, who wrote another book, Understanding Intelligence. Professor Asada, who was the president of the RoboCup Association for many years, and Professor Ishiguro, who also worked with various ideas about embodiment, and among other things came up with this robot here. It's called CB2, with many body features that are many sensors that are very interesting. So, but these are, of course, arbitrary examples for researchers who work on this embodiment concept. That I could name a long list of other people who also did many things in this field. Okay, but let's go back to Professor Kitano in the year 1997 when he wrote this RoboCup proposal. So, okay, he said in the year 2050 the best robot soccer team should be the best the human world champion in football. And okay, this is not a scientific goal, this is just something that you might propose, but of course there's also a scientific aim behind it. And then he says, foster AI and intelligent robotics research providing a standard problem. In other words, we make another benchmark. Instead of chess, we do football. Why that? And he came up with this list comparing chess with football. RoboCup stands here for football, and says, okay, in the environment, in chess is static, whereas in football it is dynamic. So the state change is turn taking in chess, whereas it is a real-time problem in football. Information accessibility in chess is complete, and it is incomplete in football because things might be occluded by other players. Sensor reading in chess is symbolic and non-symbolic in football, and the control is central and distributed, central in chess and distributed in football, because I have up to 11 players on the field, right? So if we look at these features that chess has and compare it with features that football has, we would say that the features of football are much nearer to real world situations. In the real world also the environment is dynamic, the state changes in real time, information accessibility is notorious incomplete, sensor reading is non-symbolic, and the control is of course also distributed. So we cooperate with other people, but also usually we cooperate with other people. That is a very typical feature of our everyday environment. Collection of scenes that are from RoboCup. Some of them are really old. So for example, this one is about 20 years old. This is about maybe you might call this the Stone Age of RoboCup. So this is the so-called middle-size league, and at that time basically the features of the field were color coded. So you see here in the background one of these corner posts. We talked about this already in the context of extended Kalman filtering. So we have here the combination blue color, yellow color, blue color. So this would be a corner post for the blue goal team side. So here occluded is the blue goal, and then on the other side would be yellow goal, and also corner posts with a combination of yellow, blue, yellow. Now that and these are the field player robots. These were differential drive robots with panning cameras or omnivision cameras depending on the team. And one basic requirement is that the robots are acting autonomously. So you just push the start button and then the robot has do something on its own. Kind of evolutionary development was that all the teams started to have kicking devices, and much of the performance of the team depended actually on the strength of the kicking device. So there were later limitations on these kicking devices. So let's have a look what they're doing. You see the kicking device kicks the ball, and the defender pushes it back from the goal again, and now this is already a goal. Yeah. One more time. Yeah, defender robot is doing something, but not too much. And then there comes the second attack. Goalie is the goalkeeper robot of the other team is moving a little bit too far, and this results in a goal. So this was the middle size league of RoboCup. Of course, there are also humanoid robots in RoboCup. There are several leagues with humanoid robots. That was when we were discussing inside the team what could be a future kicking device. What could be future kicking devices for our robots for the middle size league. Yeah, and then we were considering. At that time, our team was not very much in favor of this kicking device because the other people said, okay, this might destroy the opponent robots if the ball hits the opponent robot too hard. Of our games, actually, of our team in the local Japan Open competition in Tokyo at that time, the robots that you see here are now robots from a French company, Aldebaran. So in this league, there's a standard robot hardware, and the teams are only allowed to modify the software part. They are also, I will later show you, there are also other teams that where also the robot hardware is part of the competition, but in this particular league there's only the robot software different in different teams. What you also see is that at that time in this league also there was still color coding, so the ball, as we just will see in a moment, is red. They are team colors, so we have cyan and magenta for the team. And so this is on the body of the robot. We have the goal is, the one goal is yellow, other goal is blue, and so on. And yeah, so these colors are of course used by the robot to do self-localization among other things. Okay, let's see what the robots are doing. So Aldebaran, by the way, at that time had only the Now robot. Nowadays Aldebaran also produces the robot platform Pepper, and you might recognize that from the resemblance of the heads of the robot. Yeah, the Pepper robot and these Now robots, they have very similar heads. Okay. So we see the opponent team. Actually, this attacking robot is from our team. The opponent team is not doing too much. Some teams, they just have technical problems, and then the robots are just standing there in this moment. give it a little bit sound. Okay, and there is the second goal. These robots have about 20 degrees of freedom. That makes humanoid robots a much more complex platform than these robots that you saw before, the middle-size robots that usually have only 2 degrees of freedom. So this means the hardware of the middle-size robot is much more reliable, naturally. Okay, you see here a nice action from the goalkeeper robot, our goalkeeper robot. But now robot cannot stand up. Okay, now it's done. And it's high time to kick the ball away. Okay, different situation here. And another goal. Okay, so what you saw at the end was the standard platform league. This league originated from the Aibo dogs, and after Sony ceased to produce the Aibo dogs, the league had to switch to a new standard platform, and then they came up with the Now robots. Minimal system requirements for to be developed on the team side is vision processing, self-localization, ambiguous environments, motion design, behavior design, and what is good to have is a simulator that you can simulate certain situations, and then slowly the color coding of features in the game field cease to exist. So, for example, from 2013, the teams had to cope with the fact that both goals had the same color, and this, of course, much more difficult than if the goals have two different colors. The Aldebaran robot, the Now robot, had interesting hardware features: 21 degree of freedom, and Atom Z530 CPU with 1.6 gigahertz, and the camera had a resolution from 1288 times 968 pixels, and in addition the robot has various other features, for example sensors in the feet and in the head, touch sensors, a microphone. So the initial purpose of the design of this robot is human robot interaction. Yeah, and so the robot has support for speech recognition and speech synthesis, which is of course not so much used in the robot soccer competitions, but for other purposes. Yeah, I mentioned already the playground, the field, the soccer field. Here would be already two identical goal colors. It's standardized, so there's certain sizes for all parts for the goals. Also the ball is standardized, so everything has to be available worldwide. So this has to be controlled by the organization. They're always organizing committees, technical committees, who write the rule books, and a big part of these rule books are the balls, what has to be the competition ball, and what are the measurements on the field, and how big are the goals, etc., etc. Yeah, tasks I mentioned already: object recognition, localization, self-localization. So localization of the ball or the goals, mostly the ball and the opponent players. Self-localization, of course, is a challenge. Navigation and the design of motions, walking, kicking, and the goalie reactions. And overall, we have to have a concept of autonomous reactive behavior strategy, overall strategy that has to be done by the system alone. The robots can communicate with wireless networking. Yeah, solutions. What can be solutions? One standard solution for self-localization is particle filters. And at that time, where we participated at the RoboCup, the objects were recognized by color plop detection. They are fast algorithm for segmentizing the image according to the colors, and then basically we can produce a hierarchy of areas. How big is an area? The biggest red area, the biggest yellow area, and so on. And we basically, the algorithm can go through all the areas and check if any of these areas fits one of the environment objects, and then basically can use plausibility constraints to identify one of these objects. Yeah, and also one restriction for us was that we used publicly available software that was open source. This RoboCup competition has grown over the years, and many leagues have developed. So here are the groups of leagues. First group of league are the soccer leagues, and inside these soccer leagues is the middle size competition. This is the first film that I showed. Then there's the humanoid league. We will later see maybe a film that illustrates that. Then the previously mentioned standard platform league, and finally different simulation leagues. A whole network of simulation leagues, that a 2D simulation league, a 3D simulation league, or even a simulation competition league, where different simulations compete with each other for simulation features. So this would all belong to the first group. Then we have rescue leagues, different types of rescue. Also there's a rescue simulation league, but also different rescue environments which each form a league. Then there's a junior group, basically for high school students. And at that time there was only one more, that was RoboCup at home. That was basically tasks that had to be performed for robots in human environments. For example, that the robot had to follow the human, had to recognize the human, serve the human some Coca-Cola or something like that. Okay, these are now humanoid robots, some older ones, and there the teams not only build the software but also the hardware. So this was one of the challenges many years ago for these robots. They had to avoid these obstacles, the black columns, and had to walk towards the blue goal. There we see they do that. Okay. The SPL, the Standard Platform League robots, and the Humanoid League robots play against each other. This is possible if the rules allow for the same field features which was realized at one point in some year. Basically the field for Humanoid League and Standard Platform League had the same properties, so they could play on the same field against each other. And here you see one example for these games. One has to say the humanoid robots from the Humanoid League, they are much faster. These are more expensive and more powerful robots with faster motors. So SPL robots cannot win so easily. This was also a game at the Japan Open. And the now team is our team from CCU. As I said, we couldn't win this game. For the RoboCup at home competition, we also participated there in the year 2010 as a CCU team, and that was our competition robot, and there we focused on, there was a set of challenges and we focused on the first challenge is the follow challenge. So the robot is supposed to follow human and should not be disturbed by some other person. And we developed an algorithm to do that. I want to show you now the film of this algorithm, how this algorithm works. It's a video from this situation, how we tested this in the lab. The lower part is a platform that was provided from E3 in Taiwan. It's very similar to a Pioneer robot, differential drive robot. Yeah, so what this technology did was to at the lower part here was a laser range finder, and the laser rangefinder scanned surface and legs at this height have a very typical shape that can be analyzed. Yeah, and this was basically what we did. The robot tried always to keep some constant distance to its owner's legs, and could also identify them and distinguish them from other people, as we see here. Yeah, so no problem. Okay, so far so good for today. We meet online again on Wednesday. Thank you very much. See you then. Bye.